Greetings and welcome to Totality Town. 312 days until totality. This month we look at an entirely different class of eclipses. Let's talk about transits. According to Britannica, the dictionary, the formal definition of a transit is when a celestial body passes directly between a larger body and the observer. How is this different from an eclipse? After all, for solar eclipses, the moon is a celestial body and it is passing directly between a larger body, the sun, and observers here on Earth, us. Yes, but lunar eclipses wouldn't fit that definition because even though the Earth is smaller than the sun, nobody's on the moon watching this kind of event. We're still here on Earth looking out at the moon. I think the simplest way to keep transits and eclipses straight is this. Eclipses involve shadows being cast, whereas transits are all about silhouettes. We see the outline of the smaller object against a larger object in the far distance. You'll see transits in a few other places in this calendar. The general public doesn't really know about these distinctions though, so you may still hear the word eclipse being thrown around, even though it's not an eclipse. We're honestly just talking about a transit. Okay, enough with the vocabulary. There are only 3 different objects which we can watch passing between us and the sun. Mercury, Venus, the moon, and okay, we can throw the International Space Station in there. We've already talked about the moon a little bit, and we're going to save the space station for the February 2024 video. So let's focus on Mercury and Venus. Just like the moon, their orbits around the sun are tilted. So it's going to be rare that their orbits line up perfectly enough for us to see their silhouettes against the sun. This month's feature image is from the 2012 transit of Venus and was taken by NASA's Solar Dynamics Observatory. Remember that we talked about the SDO in the January 2023 video. For everyone looking at it in the Totality Town countdown calendar, you actually only got part of the image. I couldn't fit the entire transit image on the page. So here's the full-size composite showing the entire event. 2012 was during the active part of the solar cycle. So you can see all kinds of plasma loops. The SDO high-res videos of the transit are stunning, and I could sit and watch them for an hour. I love how you can see some of the small flares just popping off during the transit itself. In my opinion, the most impressive single frames are the ones where you can see the silhouette of Venus against the gases in the sun's chromosphere off the edge of the sun before the transit itself has begun. At the risk of being anticlimactic after looking at Venus, here is the SDO's view of the 2019 transit of Mercury. Remember that Mercury is a smaller planet than Venus, and it's also further away from us here on Earth. And that's why Mercury's silhouette is so small against the sun. 2019 was also at the very quietest part of the solar cycle. Trust me, I was doing a lot of solar observations before the transit, months before, months after, and it was usually weeks between even the smallest of sunspots. Transits of Mercury are still fun to watch, but you'll need a solar filter, obviously. And you're going to need a telescope because Mercury's silhouette is too small. It's really not something you can see easily with the naked eye. It'd be super easy to confuse it with a sunspot. Venus, however, is large enough to see with the naked eye when it transits the sun. I watched the 2012 transit with a piece of number 14 welder's glass. A pair of eclipse glasses would have also worked well. Transits also had a lot of scientific value back in the 1700s. Back then, astronomers could use geometry to figure out how far away objects were in relative terms, but they didn't know how many miles or kilometers away planets or other objects were from Earth. They had to operate in AU, astronomical units. An astronomical unit is the average distance between the Earth and the Sun. And astronomers still use AUs a lot for solar system astronomy today. The first person to figure out how to measure the number of miles in an astronomical unit was Sir Edmund Halley. Here's the trick though. He used geometry to develop the technique in 1667 after seeing a transit of Mercury. He realized that if two observers were widely separated on the globe and could take simultaneous measurements of the planet's position, they could use parallax to measure the AU. Parallax, for those of you who aren't familiar, is when observers see the same object appear to be in different places because they're seeing the event from different angles. Best example is this. Stick your thumb out and hold your hand out at arm's length. Close one eye, and now switch and open the other one. Your thumb will appear in a different spot than it was before because of the angle that's changed. Halley also realized that Mercury's shift was so small that you wouldn't be able to get a precise enough measurement to measure the AU. Because remember, this is the late 1600s. That's a full 150 years before cameras were invented. So they would have to use a transit of Venus instead. But that gave Halley a different problem. The next transit of Venus was almost a century away in 1761. He died in 1742, though. A number of different nations sent expeditions to different parts of the world to measure the transit of Venus in 1761, 1769, 1874, and again in 1882. But a lot of them had bad weather or equipment problems or other observing challenges that resulted in, well, not so accurate results. Astronomers ultimately found other ways to measure the AU in miles. In 2019, I organized a project called Citizen Tom for Transit of Mercury to recreate Halley's technique by measuring the parallax of Mercury during a transit. We used Daystar telescopes from the Citizen Kate project, which will be featured in the August 2023 video in the countdown calendar. And a few of the sites for Citizen Tom had solar wedges generously donated by Lunt Solar Telescopes. And we did pretty well. The final results were less than 0.5% away from the accepted modern value of the astronomical unit. This image was taken with a dedicated solar telescope during the same event. This was with my 100mm Lunt Solar Telescope, and this was one of Forbes's top 15 astronomy images of 2019. If you want to see a transit for yourself, mark your calendars and you're going to have to be willing to travel. Mercury only transits the sun an average of 13 times per century. The next one is in 2032, and there's going to be a link in the show notes with more details on that. Venus transits twice a century, and they always come in pairs. Venus will transit 1 year and then again 8 years later, and then it's always more than a century until that pair of Venus transits repeats. And the gap is very specific. It's always going to be either 121.5 years or 105.5 years. Chances are anyone watching this video, yeah, we're going to be dead before the next transits of Venus, because we had our most recent transits in 2004 and 2012, and now the next ones won't be until next century, 2117 and 2125. That means that there might be a couple of real youngsters watching this that'll get to see the next transit of Venus, but all the rest of us, we're just going to have to make do with the stunning images from the SDO in 2012, which still isn't bad. That's it for now. Thanks again for joining me here on Totality Town.